Okay, hey, this is Casey McCullough, and I am here to do the second part of the lesson on MazeSolver. In the previous video, we looked at a way to find a way through a maze using a stack. And I've updated the code a little bit since the last video just to make it a little easier on the eye and a little bit easier to use. And so you are seeing the results of those efforts. Now we have MazeSolver. And as previous, you can choose your file. There's a button to solve with the stack and a separate button and location to solve the program recursively. So now we don't have to like change the code to shift from the stack solution to the recursive solution. Now we can do it all in one screen. All right, so I am gonna start with, let's go with test file 3. This is the one I know that we can solve. All right, so we choose the file, it shows you the maze, right? We've seen this before. The white spaces are open, the black spaces are blocked. We know that. And then we go to the solve with stack button, and the red squares indicate spaces that we have tested with the stack. So we're following the algorithm that puts different squares in the stack, sees if they are the solution, and then if they don't, then it tests in various different directions, starting with the right, and then moving downward. So we sort of have this like downward, rightward pattern that eventually gets us all the way to the final square and tells us that the maze was solved successfully. Okay, so this is what we saw last time, right? And the big limitation with solving this solving a maze with the stack is that, okay, we know our way, we know that there is a way out, but if you were asked to trace your way back, if you were asked to provide a map for how you get from the beginning of the maze to the end of the maze, you cannot do that with the stack. Okay, the big improvement with the recursive solution, the reason why the recursive solution is better in this case is because once we find the solution, the recursive algorithm is able to tell us how we got there. So these yellow squares say, hey, this is the path we followed to get from the beginning to the end. Okay, notice it's probably not the optimized pattern. It's clearly not, right? We're doing a little loop here and then kind of meandering about. It is not by any stretch the most direct path we could find, but it is a viable way out of the maze. So an improvement when we solve recursively. So what we're going to do today is just walk through that recursive solution, which should be also a helpful review of recursion. And Sean is with us today. Sean, you want to chime in and remind us what recursion is?
Also, it's any function that calls itself within the body of the function, and with a smaller data set usually than the last, until it gets down to nothing.
Nicely done. Yeah, fundamentally, it's just a method that calls upon itself. And the reason why maze solving lends itself to recursion is because, let's say I put this on. We could just mark it up like this. Is because if you were like trapped in a maze and you were trying to find a methodical way to find your way to the end, rather than just like running away screaming and going, ah, just hoping that you find your way out, like the methodical,
like I would do.
Yeah, I'm sure eventually, I'm sure in real life that's what we would all do. But if we could keep our wits about us, the smart way to attack a maze would be in this methodical fashion. Let me go ahead and get my little pen here, annotate, and draw. Right, so what we would do is every time we face a choice, we would mark that so that we could come back to it. So like I'm in this maze, I immediately enter and I have a choice, right? I could go to, well, it would be my left, but let's just say from the perspective that we're seeing, right? I could go this way. There's one arrow, or I could go this way. right? I'm going to put a little circle here saying like, this is a decision point. So we choose to do one of these things first, and we follow this arrow, and then we face our next decision point. Okay. At each decision point, we're like, have we solved the maze? No. All right. Well, let's sort of mark this space and choose one of the paths. But since we've marked it, we know that we need to come back to our most recent dot. Right. And then let's see, we move on this way. Already we have another dot. So this is getting messy. And we note that, okay, here's another decision point. I'm going to trace out one of these. And if it doesn't work out, I'm going to come back to the other one, right? This is kind of the general logic behind this solution. And recursion is like, okay, well, do the next step. And if it doesn't work, we're sort of falling back to the previous step. And we'll see that maybe more clearly when we look at the actual code. So let's look at the actual code. Let me go back to my mouse here. And we'll slide this up. Here we go. All right, RecursiveMazeSolver. Here's all the code. And I'm gonna delete this and we'll sort of write it together. The work is done in a method called traverse, which is now gone. And just to see how this is actually called on, let's go to script.js and let's see. Oh yeah, okay. So when we click on the recursive solve button, we make a call to, or we create a maze using our text grid, and then we call on solver to solve it. And the method that does the heavy lifting is called traverse. And notice that traverse has a parameter. We got to pass in a row and pass in a column. So we start with 0 and 0 because that's the initial positions. And let's see, I still have my little marks here. Let me pull that out.
And the traverse method is located inside the solver?
Traverse is inside of the, sorry, this is inside
The stack.
of
Not stack.
the MazeSolver, correct.
Okay, great.
Yeah. Okay, so let's go to RecursiveMazeSolver, and I deleted traverse. Notice we already have our constructor into which we pass a maze, and we just say this.maze is assigned the value of maze. So each recursive maze solver holds a maze object.
And the maze was built, back in the maze one, right? Yeah.
Yeah. So
yeah. Okay.
You can review the maze class, take a look
And
at it.
it's a nested array or something, right? Like a matrix or.
Yeah. Right. It's a two-dimensional array.
Right. Row column. Got it. Okay.
Yeah.
Just refreshing my memory.
Yeah, no, that's okay. That is fine. Like we'll take a quick look at it. Right. It's basically storing the grid.
Right.
And
Right.
you know,
it's
what marks the
vector.
grid in terms of like squares that we've looked at, squares that are part of the eventual path. I don't want to cover it in great detail because it's covered on the previous video.
Yeah. It's all coming back to me now.
Yeah, no, it's fair. It's been a week, right? Okay, so what happens in traverse? We try to find a solution. And the first thing is we want to create a variable that lets us know when we've solved the maze. So we're going to say let done. We assign the value of false. And we're going going to say if this dot maze, I mean, the first thing, right, we're just going to be throwing a lot of positions into this traverse. And so we need to make sure that the position is valid, that it's not out of bounds, and that it is not like a square that we've tried before, or a square that is blocked, right? That is an obstacle. So we say if this dot maze, and you remember that maze has a method called try position that tells us if it's a valid square for us to be attempting.
Right.
So we say row, comma, column.
Is that the one that returns like a 2 or a 3 or a 1, that thing?
It's Boolean, right? Because it's
Oh, yeah.
yeah, let's take a second and take a look at that method, because it's important to realize what it is that we're looking at. So this .maze try position, and we pass in 2 parameters, a row and a column. And if we look at that method down here,
Try position. There we go.
the comment tells us pretty well, right? If the cell is in the bounds of the matrix, so we want to like send a false if it's not in the matrix, right? That's not going to be a useful square towards a solution. And then if we get past that little check, then we want to check if the cell is not blocked and not previously tried. And those can be, rather than trying to eliminate the cells that are blocked, which are zeros, and those that are previously tried with a 2, we can basically just say like, we're looking for ones. We're looking for those squares that are valid paths that we have not yet tried. So only those squares that are in bounds and haven't been previously tried result in a true. And so,
Right. Okay. Yeah. It's checking. Okay. Okay. Makes sense. Yeah.
so that's all we're doing here. We yeah, want to confirm that they're legitimate spaces.
Valid position.
And just
Oh,
for
I was
our
thinking
own,
I was thinking of the try thing. That's what I was thinking of. Tried. Okay. Got it.
just for our own purposes as developers, I like to put a little console.log and say a valid position, just so we're getting that information in the console. You can take that out later if you want.
We're done. Valid position or try position? It's valid position, right? Am I crazy?
Oh yeah, valid position, sorry, yes.
Okay, that's what I thought.
Thank you for the catch, valid position. Okay, and if it's valid, the first thing that we want to do is to mark it as a place that we've tried. So this is where we call on this
Oh boy,
dot
I'm in Python
maze
mode. It's so hard going back.
try position
Okay.
row column. Now it's marked as tried, which basically means putting a 2 there, right? 2 is the way
Right.
that we indicate that that the square has been tried. All right, so how do we know if we've reached the solution?
That was a. Oh, reaching the bottom right corner.
Reaching the bottom right corner, yeah. And
max length
obviously we're talking to the maze to find out what is the bottom right corner. So Sean, do you remember how we can sort of write that as code?
Well, it would have been the max length of the matrix on both ends. So.
Okay, good. So let me get it started. We're going to start with the row side, right? We'll say row equals. And who do we want to talk to find out information about the row and column with respect to their position in the maze?
Well, the row, just the first thing. So you could just do 0 dot length, I think, right? The maze.
Yeah, so we need to talk to the maze,
yeah,
right?
the
So
maze. Sorry, that's I'm getting ahead.
Yeah.
So if row is equal to this dot maze, and then you want to look at the first row's length. Well, any row's length technically, but.
Okay, good. So yeah, we can say this dot maze. Actually, we have built-in methods that we wrote previously.
That's right.
So last week we wrote those. One is called get rows. So we can just use that. minus
That's
1, right? That's the last valid row.
Okay.
And
then get column.
Column also needs to equal
Uh-huh.
this dot maze dot get columns. I think we use the full word columns minus 1. Right. If that is true, then we're done. So the main thing we need to do here is just to say that done is assign the value of true. And that's going to enable us to skip out on all of the heavy lifting that's involved in this recursive solution. Okay, so the next part of the solution is going to look kind of like the stack solution, in that if we haven't found a solution, we want to try in all 4 different directions. But the way we set it up is going to be a little different from stack, right? What do we know about the done variable? We know we assigned it false in the beginning. We know that we've just assigned it true if we know that we've landed on that final square. But what can we say if we haven't assigned it true? Do we know it to be false?
Or
do we know that
inside this context, yeah, because it hasn't changed from false inside here.
Oh, right. So the variable will be false, but do we know that we have tried every possibility and therefore we're done? Like, I'm phrasing the question awkwardly, so it's not you, but all we've done within the context of this method so far is just tested 1 square, right? And that square isn't the bottom right square. So
we can mark that. So we can mark that one as, oh no, it's already marked as tried. Never mind.
Yeah. So what we need to do is to say, well, we don't have an answer yet. We need to try some more squares. And so done needs to be sort of passed on to those next squares. So here's where the recursive part comes in. We're going to say, I'm going to punt. I don't know the answer to done, so I'm going to let these other methods answer what the value of done should be. And these methods are going to be additional calls to traverse. So we say done is assigned the value of this dot traverse. And now we want to test, well, let's do it sensibly and let's test down. We know we have to go down. So let's test the position that is down from row and column. So Sean, what do you think? What would the code?
Row and then call -1. No, call +1. No, I'm sorry. Row plus 1.
Row plus 1, right? I know it's not super intuitive, right? Row plus 1 means we are physically going down in the rows, which means lower on the screen. So yes,
I've never been able to remember which one's row, which one's column. Like, just the words mean nothing to me. I'm like, I know one goes one way and one goes the other.
I know.
I have to really.
I still have to review it in my head every time. So we could say row plus 1 column, and since we are figuring this out, it's good to write a little comment here that just says down.
Cool.
Okay, and it is possible that that has solved it. So we want to say if not done, then we want to evaluate, say, to the right. Right, we'll start with down and to the right, since we are starting the upper left and moving to the bottom right. That's probably the most logical progression to follow. So we say this dot traverse. Oh, sorry, we can say done. Should say done is assigned the value of this dot traverse. And now we want to try to the right. So that means our row is going to be the same.
And column plus 1.
It'll be column plus 1, exactly.
can't stop writing in Python. I keep putting or colons instead of brackets.
I know. I used to like, I'll be trying to write Java code forever. That's just where my brain goes. Thankfully, it's pretty close to JavaScript for this kind of stuff. Okay, so oh yeah, let's put the comment that says that like this is testing a square to the right. So we're launching another recursive call, testing the right square, and then we can just copy paste this, because after testing the right square and we've tested down, now let's test, I don't know, let's test up. So up, counterintuitively, if down is row +1, up is going to be row -1. And we want the regular column. And finally, what's left? We've got up, and we want left. And left is going to be the opposite of right. So it should be row and then column -1. So now we've tested all 4 possibilities. And each one of these calls will just continue to hand things off to the next call and the next call and the next call. So we'll continue testing until either they hit a situation where they've tested everything, every branch of the maze that extends from this given position, or they've reached the solution. And so after this else clause, now we evaluate whether we have solved things or not. So we can say if done, we can say this dot maze dot mark path row comma column. And if we go back to the maze class, you'll remember that mark path is our way of assigning maze.path, which is just the number 3.
What was that? Scrolling back down there. Sorry, I missed.
Sure.
I was writing something.
Here.
No, back down to the code. The if done.
Back to RecursiveMazeSolver.
Yeah, I just missed the where we were. Okay, mark path. That's what we did. This minute. Okay.
All right, and remember, the important thing to remember is like this is marking the row and the column for 2 individual values. But remember that we have all of these hanging previous calls, recursive calls to traverse, and they all have their own set of row and column that are hanging around waiting for a response. And so when this variable gets flipped to true, then that same variable gets flipped to true for all of the prior calls. And so once done is flipped for one of those squares, it is going to be flipped for every square from the previous recursive calls. So this will not, big picture, this will not just mark one square, it will mark the entire path, as we saw in the beginning of this with those yellow squares.
Okay, interesting. Let's.
And finally, there's one more step. Let's see, we need to. The way we communicate that back to the prior calls is we say return done.
What return done at the end? That's already there. Yeah. Okay.
Yeah. All right. So this is the solution, and if we save it and we go back here, well, there's no sense to demo it. It's the same demo that we did before, right? But this is the path that is marked with those threes is the path that is marked as
Oh,
path. And that's why it's marked out in gold.
I spelled something wrong. Mine's not working. Valid. Valid. There we go.
So yeah, let me know when that works for you, Sean, or if you have any questions.
Huh. I clicked it too
I
many times.
am going to go ahead and shut the video off.
Yeah,
Um,
it worked. It's another one of those cases where recursion just breaks my brain because I don't know how it worked, but it worked.